Section 2.8 now talks about the derivative as a function. So I talked about this a little bit in class. We have already worked with these two definitions, okay, the first two, that stand for what? The derivative. F prime of A is the derivative at some value, at some x value A. So A is a number, okay, and I have two different definitions to use. Now we're just going to say, well, the derivative of a function, f of x, is f prime of x, instead of looking at a number. The definition here would be the limit as h goes to 0 of f of x plus h minus f of x all over h. Only difference is instead of a being an actual value, now I'm looking at x as the variable. Now I'm finding the derivative of, say, x squared in terms of another function. Okay, there's my first example, x squared. I want the derivative. So f prime of x, that's the derivative, would be the limit as h goes to 0 of f of x plus h. So I'm going to do x plus h squared, okay, minus x squared all over h. So f of x plus h, f of x. F of x is just the function, the original function. Now I simplify this, so I would have limit as h goes to 0 of FOIL x squared plus 2xh plus h squared minus x squared all over h. The x squareds cancel. You could factor out an h, cancel that. So factor out an h, and I'd have 2x plus h over h. They cancel. Now I can plug 0 in for h, and I get 2x. So the derivative of x squared is 2x. Okay, notice. I start with x squared. It looks like this. The derivative of that is just a line, 2x. Whoops, sorry. Up 2 over 1. So here is the original function, and the derivative is just a line. Okay? Another example with x cubed minus x. I'll probably just set this one up. So f prime of x will be the limit as h goes to 0 of f of x plus h. So I would have x plus h cubed minus x plus h. Okay, that's all f of x plus h minus f of x cubed minus x all over h. Make sure you distribute this negative. This would be, I would have to multiply it out. You could use Pascal's triangle to do that quickly. Okay, and your answer should be 3x squared minus 1. Okay, so if you do that all out, you should get 3x squared minus 1. Okay. Next problem is with a square root. I want to try to find the derivative of the square root of x. So f prime of x would equal the limit as h goes to 0 of f of x plus h. So this is x plus f of x plus h minus f of x all over h. Okay, now to do this I'm going to rationalize. I've already multiplied by that. Come over here. I'm going to simplify. So the numerator would be x plus h minus x. The denominator would be h times the square root of x plus h plus root x. Okay, the x's are going to cancel in the numerator, the h's are going to cancel, so I'll get the limit as h goes to 0 of 1 over the square root of x plus h plus root x. Now I can plug the 0 in for h, and I would get 1 over root x plus root x, which is 1 over 2 root x. So the derivative of root x is 1 over 2 root x. Next problem, I have a lot of the work done out already. So I have a rational function, okay, and I have the limit as h goes to 0 of what? F of x plus h. So this first whole term is x plus h. This is f of x all over h. I'm going to have to find a common denominator. So the common denominator with the numerator would be this. Okay, it would be 2 plus x plus h times 2 plus x. So I multiply the first fraction by 2 plus x, and I multiply the second fraction by 2 plus x plus h. All right, I've done that step out, and then I've jumped to the answer. So I've multiplied this out. I multiplied the second one out. Now you just have to combine like terms and cancel. And my answer should be negative 3 over 2 plus x squared. Okay, this algebra is very, very similar to what we're doing before. Okay, next problem. Now I have an actual velocity problem. So I'm given the position of a function, okay, 1 over 1 plus t, where t is measured in seconds and s is in meters. Find the velocity and speed after 2 seconds. So the velocity is really just the slope of the tangent line at 2. So this problem really just wants me to find f prime of 2. Okay, so now I actually have an a value. So a is 2. Okay, so the point is 2, and if I plug 2 in, I get 1/3. So my point is 2 1/3. So I have the f prime of 2 would be the limit. I'm going to use h. As h goes to 0, now I can actually use f of a plus h. So now I could use what? 2 plus h. So I could plug 2 plus h into the function. So I'd have 1 plus 2 plus h. That's f of a plus h. Minus, okay, f of a, which is 1/3 over h. So this just becomes limit as h goes to 0 of 1 over 3 plus h minus 1/3 over h. I'm going to find the common denominator. So I had the limit as h goes to 0. My common denominator would be 3 plus h times 3. So I'd have 3 minus 3 plus h over 3 plus h all over h. When I divide like that by h, the h is just going to end up there. So I have the limit, because you're multiplying by 1 over h when you flip it. So I'd have the limit as h goes to 0. 3 minus 3 is going to cancel. I'm going to get negative h over 3h times 3 plus h. The h's cancel, so I get the limit as h goes to 0 of 1 over 3. I'm sorry, negative 1 over 3 times 3 plus h. Now I can plug 0 in for h, and I'd get negative 1/9. Okay, so my velocity is negative 1/9 meters per second. My speed is just 1/9. So all speed is the absolute value of velocity. It's always positive. So my velocity is negative 1/9. My speed is positive. All right, the second thing you're going to be asked to do is given a graph. Now sketch the derivative. So the algebraic problems, you were finding the derivative as a function. Now here is sketch the derivative. Okay, so now in order to do this, you really have to think of slopes of tangent lines. Okay, so what do I mean by that? If you think about this graph over here and you say, okay, at what values, so down here, at negative 2, the slope of the tangent line, if I drew it, would be horizontal because it turns. So that means the slope of the tangent line at negative 2 would be 0. So that means the derivative graph at negative 2 would be 0. Okay? Another one is just before 1, same thing. At 1, just before 1, the derivative. So this is the original, this is f of x, and we're sketching f prime of x, the derivative, which means the slope of the tangent line. So you're sketching a graph in terms of all of the tangent slopes. Okay? Now if I come over here to the left of negative 2, if I were to draw tangent lines, they would be negative because the function's doing what? It's decreasing. Okay? So over here, my function is going to be negative. Okay? It's going to be down here because those are negative values. Now after negative 2, okay, what happens? Now if you draw the slopes, they become positive and they become more and more steep until about negative 1, then they become less steep again. Okay, so I know my graph is positive at about, and then at about negative 1, they get less steep again, which means they come back down, the derivative. Okay, and now if I come over here, I have what? I have negative slopes, negative slopes, negative slopes, and it turns again just before, I would say, 3. So at 3, it's going to be 0 again, so it's going to come down and come back up. So there's a sketch, not exact. I don't know exactly how high it goes, okay, in between -2 and 1. There's a sketch of the derivative, just based on slopes of tangent lines. Okay, do another one. Simple parabola. So first thing you want to do, easiest thing to do, is look at what? Where the slope would be 0. Anytime it has a turning point, a local max or min, the slope would be 0. So it's going to be 0, 0. Okay? Now if you think about it, everywhere to the left, over here, the slopes are all negative, because the parabola is going down. Over here, the slopes are all positive. Now, they're just getting, if you think about this, less and less steep coming from the left. So that just means it's going to be coming closer and closer to 0. So say this slope is -4, -3, -2, -1. It's just coming up because they're getting less steep. And on this side, they're getting more steep as you get higher and higher. So the derivative of it is just a line. Derivative of any parabola is just going to be a line. I have 2 more to sketch the derivative. You can try at this point to sketch this next one, simple polynomial. So, what do we have to start? We know that, what? Here and here, it's going to equal 0. Okay, so at -1 and 1, I'm going to be 0. I know that to the left of -1, when x is less than -1, if you come over here, they are all negative slopes. Okay, so over here, it's going to be coming up. And I know in between -1 and 1, they are positive slopes. Okay, and about 0 is when they flip. That's the hard thing to vision. But you could think between -1 and 0, they're getting higher and higher and higher. The slopes are getting steeper. And then between 0 and 1, they get less steep again, but they're still positive. And then after 1, now the slopes turn to be what? Negative values. So, okay. Again, you start with a cubic, x cubed. You should know that the original graph isn't a cubic. And your derivative, if you look, is a parabola, x squared. All right, last one is a little different. Absolute value you should recognize. So we recognize this graph as the absolute value function. Okay, so how am I going to sketch the derivative of that? So if you think at 0, there isn't a derivative, and here's why. To the left, it's just a line, so all of these slopes are the same. And if you look, what are they? Down 1 over 1, down 1 over 1, because this is a line. So the derivative is equal to -1 for any x value less than 0. It actually equals -1, because derivative is just slope of tangent line. Okay, to the right of 0, it just equals +1 here. Now I'm going to talk about this in a second. Why is that an open circle? How come it doesn't have a derivative at 0? Well, you can think about it. How would you draw the tangent lines? Same idea as before. From the left, they'd be -1, and from the right, they'd be +1. So the derivative, it's not going to be able to have a derivative at 0. Okay, so this is just some other notations that you'll see with derivative. Okay, so f prime of x means the derivative. Y prime means the derivative. dy over dx, that is the exact same thing as f prime of x or y prime. Okay, df over dx, same thing. And then d over dx, f of x. So this is just notation for you to realize. dy dx means the derivative. Okay, and then this notation down here means the derivative when x equals a. So this is find the derivative and then plug a number into it. Okay. The last thing we have to talk about is what makes something differentiable. What makes something have a derivative at certain values. Okay, and I just want to quickly review continuity. So it's continuous. What are your 3 rules? It's continuous if what? If f of a exists, if the limit as x approaches a exists, and then if what? It's continuous at a if f of a equals the limit as x approaches a. Okay, so we know that from before. Now, a function's differentiable at a, at a number, if f prime of a exists. Okay, if it is differentiable on an open interval from a to b, or from a to infinity, negative infinity to a, or negative infinity to infinity, if it's differentiable at every number in that interval. It's pretty basic. All right, so to show where a function is differentiable, we need to find the derivative at a certain number or on an interval. So for absolute value, where is the function differentiable? So I would have to split this up, okay? I would have to say f prime of x, using my definition, would be the limit as h goes to 0 of f of x plus h, there's x plus h, minus f of x all over h, okay? So now we'd have to split it up. Where would we split it up? We'd split it up at 0, okay, because that's where this is defined. So I'd say for x is greater than 0. When x is greater than 0, what would this actually become? This would be the limit as h goes to 0 of x plus h plus x all over h. Okay, it would just be itself. It would be x plus h inside the absolute value, and it would be x. And then I'm sorry, minus. I mean, typo there. That would be, sorry, make sure, go back. That would be minus x. Okay, so the x's would cancel. I'd get h over h, which is 1. Okay, now for x less than 0, this would become the limit as h goes to 0 of negative x plus h, okay, minus negative x all over h. It would be the opposite values inside the absolute value. Now I could simplify that, simplify the numerator, and the x's are going to cancel. You're going to get negative h over h. Okay, oh, the limit almost caught me as h goes to 0 of negative h over h, which is negative 1. Okay, so what is this saying? So these don't have to be the same. These have a value. So it is differentiable when x is greater than 0. From 0 to infinity, it's differentiable because it has a derivative, 1. From negative infinity to 0, it's differentiable, okay, because I get negative 1. Now you have to test at 0. Okay, so now I would say at x equals 0, and I would say, well, what's f prime of 0? Now I'm actually testing at an a value. So now I would have the limit as h goes to 0 of f of a plus h, which is 0 plus h, minus f of a, which is 0 all over h. And this would become, if you plug this into your function, this would become the absolute value of h over h. Which now, how do I find the limit of an absolute value? Now I have to do it from the left and from the right. So now I would say the limit as h goes to 0 from the left would be negative h over h, which is negative 1. And the limit as h goes to 0 from the right would be h over h, which would be 1. So I am not differentiable at 0. Okay, why? Because the derivative equals negative 1 from one side and 1 from one side. Yes, we already knew that, the absolute value. So f prime of 0 does not exist. So it's only differentiable for less than 0 and greater than 0. Okay. Big idea. If f is differentiable at some number, then it has to be continuous. Okay, so if it has a derivative at a number, then it definitely has to be continuous. Now, the other way around is not true, because we just saw absolute value is continuous, but it's not differentiable where? At its point. Okay, and then how can something not be differentiable? There's 3 ways that something is not differentiable. The first is called a corner. And graphically, all that means is that the left and the right will not be the same, okay? So I have a corner, which I could think of a corner as absolute value, or the function could actually be, curved a little bit. So at this value, it's not going to be differentiable. I could have a discontinuity, okay? So if it broke or jumped, then it would not be differentiable at that value, okay? And then the last one, I could have a vertical tangent. Vertical tangent. So the graph just drops very quickly. So I would not be differentiable at that x value because the tangent line, if I tried to draw it, would be vertical. Those are the ways that something is not going to be continuous at a specific number. Last thing, higher derivative. So f of x. In particle problems, f of x always stands for my position, the position of the particle. F prime, the first derivative, stands for what? The derivative of position is velocity. Okay. And the second derivative, which I could f double prime, f with two little marks like that, is what? The derivative of velocity is acceleration. We'll talk about this more in class. Acceleration. And then notations used. Position is usually s of t. Velocity is v of t. Acceleration is a of t. We'll talk about that more in class. And then for examples, you could find second derivatives or third derivatives. How would you do it? You would find the derivative of f using the definition, and then you take that answer and find the derivative again. Again, we'll do this in class. I won't show this, but I just wanted to show that we can find higher derivatives. We can find second derivatives or third derivatives. I would just have to use that formula more than once. Okay.